All right, well, let me talk a little bit about your midterm exam, which will be next week, okay? All right, so I'll have a list of topics online that I think would be relevant or that you should know. It's going to be 35 multiple choice questions. You'll have 90 minutes. Okay. You are allowed, so bring your reference tables.
Sorry, what?
Bring your reference tables. And you can have one letter-sized paper with notes on one side. Let's see. Okay, and then we will have lecture after the test. So my apologies. I know nobody wants lecture after the test, but we will have that. So okay. Are there any questions or issues? Yes.
Do we need a Scantron?
No, I will provide you with Scantron forms. Okay. I guess answer forms. Okay, so okay. There any questions here? So today what I'm going to cover is I'm going to do a wrap-up of Chapter 6. Here, let me get the video started. Okay, no, it's still running. So today, wrap-up of Chapter 6, and then I'm going to intro Chapter 7. All right. But the midterm only covers through Chapter 6, okay? So what I cover in Chapter 7 will not be on the midterm, okay? So wrap up Chapter 6. This will be on the midterm. Chapter 7, not on the midterm. Okay, and then after I intro Chapter 7, then I'll just do a brief review of midterm topics, okay? So I'm gonna, so I know this, it feels a little awkward putting this here, but I want to at least introduce the Chapter 7 topics, and then next week after the midterm I'm going to explain a lab. So lecture after the test, I'll be doing a lab demonstration, kind of showing how confidence intervals kind of work in this repeated construction of confidence intervals way. Okay. All right. Questions, issues, comments? All right. Then let's move on. Okay, so let's just recap or review of confidence intervals so far. Yes?
Brandon, in terms, is it going to be questions similar to the quiz, just multiple choice, or what can we expect in the quiz?
Yeah, I guess this is a hard question to answer because, so I write the quizzes and I write the midterms, so they're coming from my brain, so in that regard, I feel like there's going to be some similarity. I feel like the questions are very fair regarding the content covered. Yeah, I'm not sure how to answer. I think, yeah, studying the homework. Well, I'm not sure how you feel, how the homework and the quizzes, how they mesh, whether they're comparable in terms of content covered, or if there's a disconnect there. It's my intention that they're at least connected and related. So, of course I'm going to think this, but I think the questions are fair on the exam. So, okay. Is that all right? Okay. All right. So let's let's just go over confidence intervals. Okay. So far we've created a confidence interval for what population parameter? So it's a confidence interval for mu. So the population mean. Okay. Based on a sample. Okay. And in particular, the part about the sample is based on a sample with X bar. Okay. So the idea being, we observe a sample, and based on the sample, what can we say about mu? So the idea, big idea, so just so we don't lose sight of the big picture, we observe a sample, based on what we see in the sample, what can be said about the mean of the population. Okay. And there's two key parts that we look at in the sample. Okay, so we see the sample mean X bar, and we say the population mean, mu, should be close to X bar. Okay. And the idea of close to X bar depends on the amount of spread we see in the sample. Okay, so we see S and use that to estimate how close we can expect mu to be. So this is the big picture idea behind confidence intervals. Yes?
Could you dim the lights on?
Oh, dim the lights. Sure. Okay, so key thing, our confidence intervals are always about the population parameter. All right, are you guys, it looks like you guys are still writing, so wait. Okay, and so when we, the construction of the interval goes something like this. We put x bar plus or minus t star times the standard error. Okay, or actually, let me, instead of write standard error, let me write s over the square root of n. So this is our, at the center of the interval, this is our point estimate of mu. So observing only our sample, our best guess for mu is x bar. This is our point estimate of mu. This part over here, this is known as the margin of error. And the margin of error, it consists of two parts. There's the critical value, t star, which decides how much cushion we need, okay, kind of. Okay. And then s over the square root of n, this is known as our standard error. And it's essentially an estimate of the standard deviation of the sampling distribution. Okay. And just a quick check of our understanding, what is a sampling distribution? Or if I wanted to say the sampling distribution of x bar is, what is that?
The distribution of the means of every sample taken?
Yeah, it is the distribution of all possible sample means of all possible random samples that can be taken. Okay, so this is of all sample means from all possible random samples. I should say from the population. Okay, and the central limit theorem says the sampling distribution of x bar follows the normal distribution. So far, so good. I'm hoping this is all feeling okay. So, as far as reviewing what we covered last week. Can you read the bottom lines okay? Okay, so we're going to then take this idea and extend it to 2 samples, okay? Okay, so extending ACI to make inference from 2 samples. Okay, and so the idea here is we have, sample 1. Okay, sample 1 comes from group 1. So whatever group 1 is, maybe you want to take a sample of males and a sample of females and see if there's a difference between them. Do males overall have higher or lower cholesterol than females overall? Maybe, maybe not. Who knows? Do males overall have different this or that? So you got 2 groups, group 1 and group 2, and so we've got sample 1 coming from group 1, and we have sample 2, which comes from group 2. Okay, and in sample 1 we have mean x bar 1, standard deviation S1, and size N1. In sample 2 we have x bar 2, S2, and N2. Okay, and we don't expect any of these to necessarily be the same. So, okay, so actually most likely x bar 1 and x bar 2 will be different, okay? So in nearly all cases, x bar 1 and x bar 2 have different values. Okay, and what we want to know is, does the fact that x bar 1 and x bar 2, the fact that they're different, does that then indicate that the respective population, group 1 and group 2, have different population means? Okay? That x bar 1, I'm going to just write, is not equal to x bar 2, then indicate that the respective populations have different means. Okay, so that is, does it mean that mu1 is not equal to mu2? That's what we want to know. Okay, so for example, perhaps we wanted to say, we have a question. Is the average IQ of men different than the average IQ of women? Okay, we take a random sample of 50 men, random sample of 50 women. Okay, maybe one sample, the average IQ is 100 points, and the other sample, the average IQ is 101 points. Okay, so there's a point difference. Does that indicate that in the respective populations there's actually a difference between the average of group 1 and the average of group 2? That's what we want to know. Okay, And so with something like that, we're probably inclined to say, you know, we observe a 1-point difference between sample 1 and sample 2, but probably in the grand population, we're not going to observe a difference. Or we might not necessarily observe a difference. On the other hand, we could ask something like, is the average height of men different than the average height of women? Okay? And we take maybe a group of 30 men and a group of 25 women, it doesn't matter. And we get the average height of the men to be something like 5'10", the average height of the women to be something around 5'5". Okay, so we observe a 5-inch difference. Is the 5-inch difference between our two samples then indicative that the populations are different? Okay? That's essentially what we're asking here. All right, and so what we're going to do with our information here is we are going to make a confidence interval for the quantity mu1 minus mu2. Okay, so we're going to make an interval for this quantity, which is the difference between the means and the population. Okay, so for example, what do you think a plausible range, if, for example, if we're talking about IQ scores for men, which we'll call group 1, and women, which will be group 2. Okay, now we haven't collected any data, but just what kind of range, what might we see for a confidence interval for mu1 minus mu2? We're asking, what's a plausible range of values if we were to take the difference between male IQs and female IQs? Okay, let me, we'll break this down. What would you expect if I took a random sample of male IQs and a random sample of female IQs, and I took the average of the men and then the average of the women? How do you think those averages would compare? Do you think one? They're going to be about the same, okay? So we're expecting, we would probably expect this to be close to 0, but if we were to look in the population, probably, the average IQ of men and the average IQ of women, it could be anywhere from, minus 10 to plus 10 or something like that, if there's, depending on our sample, okay? So, we expect the center to be around 0, close to 0, and then we will have some margin of error. Okay. Conceptually, does this make sense? That our confidence interval for mu1 minus mu2, we're anticipating the center to be around 0 when it comes to IQ scores. Well, at least in the US, where men and women have generally equal access to education, right? Thinking. Okay, so if, on the other hand, if we were to make a confidence interval, so if we make a confidence interval for mu1 minus mu2, and let's say we were talking about heights. Okay, you know, what do we expect to see in the middle? To be the center of our interval. Any takers here? So if somebody said, you know, take your average male, so the height of your average male and the height of your average female, what kind of difference are you expecting there? 5 inches, something around there. Okay, so we're expecting the center of our interval to be, you know, about 5 inches. And then we're going to have some kind of margin of error, right? Okay, so we'll extend this, and we're going to do, you know, so creating a confidence interval for the quantity mu1 minus mu2. Okay, so at the center of our interval, we're going to put our point estimate for mu1 minus mu2. Okay, and that's going to just be the difference between our two sample means. This goes in our center, and this is our point estimate for the quantity mu1 minus mu2. And then we're going to go plus or minus t star times our standard error. Okay, so again, this is going to be our margin of error, which is our critical value, times our standard error. And the standard error is just going to be a little bit ugly, but it's not so terrible. So our standard error is just this quantity. So if you, something that people help use to help remember is just imagine these being the sides of a right triangle, and here you've got standard error 1, which is s over the square root of n, or s1 over the square root of n1. And standard error 2, which is s2 over the square root of n2. And so this is going to be, you know, a squared plus b squared equals c squared. So this is the square root of se1 squared plus se2 squared, which is exactly what we have here. Okay, but it essentially it follows the same form as the confidence interval for 1 mu, right? For a single mean of a population, we put our point estimate in the middle, plus or minus some margin of error. The margin of error being the critical value times the standard error. Okay. Is this okay? All right, so let's try this out. Okay, so we'll look at IQ scores. So So sample 1 will be men, sample 2, women. Okay, and so I'll say 20 men, 25 women. X bar here we'll say 100.2. Standard deviation 15.6. X bar 2 101.3. S2 16.5. Okay, so we're going to make a CI for mu1 minus mu2 based on our two samples. Okay, so our current point estimate using the data that we have is going to be x bar 1 minus x bar 2. So I have 100.2 minus 101.3. I get a mean difference of negative 1.1. Plus or minus t star times our standard error, which is s1 squared over n1, plus s2 squared over n2. Okay, so how do we selecting t star? Okay, so the truth is the degrees of freedom for t star is difficult to determine. So we're just going to kind of wing it with an approximation. So the actual degrees of freedom for t star is rather difficult to determine for this kind of situation. So we're going to use degrees of freedom for t star. We will use this it's going to be n1 plus n2 minus 2. This is going to be a generous degree, give us a generous degrees of freedom. Okay, so this is a quote-unquote generous approximation. The actual degrees of freedom is almost always less than this. So because we're getting a generous value here, in this case it's very important we always round down. If we do not find the exact degrees of freedom in our table, okay, there is, depending on the textbook you read or class or teacher you have, some might encourage using kind of the safe or the stingy approximation, which would be n minus 1 using the smaller of your two n's. So whichever n is smaller, do n minus 1. So the stingy approximation would be 19 degrees of freedom. Our generous approximation would be 43 degrees of freedom. Okay, and so the true value is going to be somewhere in between there, depending on your standard deviations, believe it or not. Okay, so in our case, so we will approximate with degrees of freedom equal to n1 plus n2 minus 2. So we get 20 plus 25 minus 2, 43 degrees of freedom. Okay. So if I'm going to make a 95% confidence interval, how many degrees of freedom, or what is my t star going to be? What is the t star that I will use? So I'm going to use 2.021. Are we agreed on there? So find 40 degrees of freedom in our table with 95% confidence. We get 2.021 as our T-star. All right, and then now I'm going to just plug in all of our S and our N values. 15.6 squared over 20 plus 16.5 squared over 25. So I'm going to do these calculations. I got negative 1.1 plus or minus 2.021 times 15.6 squared. So try this out on your calculator. Make sure you can get the same answer I get, in case we have some calculator discrepancies here. So I'm getting 2.021 times 4.802, basically. .705. So I encourage you guys, if you have your calculators with you, which you should have because you just took your quiz, just make sure you can punch this into your calculator and get the number I'm getting, 4.802. Are we okay there? Okay, and so multiplying that by 2.021, I get 0.9705. So if I expand this and I do negative 1.1 minus this, I get negative 10.805. And then I do this. Oops, that's not. Plus 9.705, 8.605. Everyone's so quiet. All right. Okay. So then let me take these values. So this is my confidence interval. And let's write our interpretations. So this is, excuse me. So our 95% CI for mu1 minus mu2. Okay, so what does this mean? So our interpretation. Okay, we can say something along these lines. All right, so this is I am 95% confident that the difference between the mean IQ of men and mean IQ of women is between negative 10 point, I'm just going to round off to 10.8 and 8.6 points. All right, this, I'll let you guys finish writing that, but this feels not very clear. So I'll try writing it in another way, which is going to be, I am 95% confident that the average IQ of men is between 10.8 points lower and 8.6 points higher than the average IQ of women. And I don't know if this one's any easier to understand here. So if somebody were to ask you, okay, you took two samples, a sample of men and a sample of women, and you observed a difference between their average IQs. And they ask, do you then have evidence, do we have evidence that the average IQ of men and women are different? IQs of men and women in the population are different. Okay. How should we answer this question? So our answer to this question is, what is it? No. So our answer is no, okay. The value 0 is in between the bounds of our interval, okay? Meaning 0 is a plausible value for mu1 minus mu2. 0 is within our interval. Okay, so 0 is a plausible value for the quantity for mu1 minus mu2, meaning it's very possible that the true difference between the average IQ of men and the average IQ of women is 0, or that there is no difference between the average IQ of men and women. So this indicates that it is plausible that the average IQ of men and women are the same. If somebody then asked, do we have evidence that the average IQ of men and women are the same. How would we answer this question? Yes? No? No. Okay, so our answer here is no. And why is our answer no? Okay, so our data doesn't indicate to us that they're different, but that does not indicate that they're the same either. Okay, we basically just looking at 20 men and 25 women or something like that. That's not going to be enough to prove that the population means are the same. And in fact, we cannot prove that the population means are the same until we actually know the population means. All right, so no, we write our data does not show that they are different, but that does not indicate they are the same. Okay. So a lot of times in statistics, we just come to these conclusions of we don't have enough evidence to say one thing or another, okay? And that's actually most of life, really. It's just if somebody asks you to prove something based on evidence, it's difficult to truly prove something, okay? The only really way to prove things is logical deduction, or having all the evidence necessary. And if you don't have all the necessary evidence, it's difficult to prove one thing or another. But you might have enough evidence to say something. So, but yeah, that's how it goes. Okay. Why don't we take a short break here? We'll come back, start chapter 7, and then we'll transition back into a review for the midterm.